Hello, friends. We're talking about acids and bases, and today we're going to talk about the strength of these acids and bases. Strength, meaning either strong or weak. It's kind of a counterintuitive idea in chemistry. Let's see what we mean. One of the easiest way to look at the strength of an acid is to see how well that acid conducts electricity. And so if I put an acid like HCl into a beaker of water and then run a circuit that lights up a light bulb, I will see that that light bulb is going to be really, really bright when HCl is in the water. It conducts electricity exceptionally well. On the other hand, if I take another acid, seemingly no different than HCl, this time HF, and I put it into water, the conductivity is there, but it is much less there than it was in HCl. The bulb isn't as bright. So it still conducts electricity, but just not as well. One one way we would characterize each acid is as an electrolyte. Electrolytes conduct electricity, and HCl would be considered a strong electrolyte. And HF would be considered a weak electrolyte. Doesn't conduct electricity as well as a strong electrolyte. There are also things called non-electrolytes that don't conduct electricity at all. Sugar is an example of that. So the question becomes, what makes something a weak or a strong or a non-electrolyte? Really has to do with something called percent ionization. How well does a particular um, acid, in this case, ionize when we put it into water? So what I mean by that is if you take a look at HCl, when you put it into water, it acts like a Bronsted-Lowry acid. We learned about that concept yesterday, where it delivers an H plus to H2O, and we end up with Cl minus and H3O plus in solution. At the same time, if I look at HF, it does the same exact thing, seemingly. HF, you put it into water. Water is, in this case, a Bronsted-Lowry base. Hydrogen from HF goes to H2O, and we produce F minus and H3O plus. At first glance, they don't look to be any different at all. But look in the beakers here. Let's take a look. Let me change my color. If I look at this beaker right here, literally the only thing that's left in the beaker are negative Cl minus ions and H3O plus ions. In other words, all of the HCl ionized, and I'm only left with Cl minus and H3O plus. If I asked you about the percent ionization of HCl, you would say 100% ionized. Okay. On the other hand, if I look at HF, the story gets a little bit more complicated. Take a look inside of the beaker. In the beaker, I still have water molecules. I have F minus molecule ions. I have H3O plus ions, but I also have some HF that never broke up or never ionized. So we would say that weak electrolytes, weak acids, don't ionize completely. So, what you would say in looking at this equation to differentiate it from the one above, the percent ionization is less than 100%. And typically, the ionization that we see is actually around 1 to 5% ionization for these weak electrolytes or weak acids. So, how do I tell the difference in the equation itself? Well, the primary way is looking at the arrows. If I look at HCl, it ionizes completely to Cl minus and H3O plus. They cannot react and come back to form more HCl and water. And so it stays only on the product side. We only get ions in solution. But for the most part, F minus is pretty good at collecting a hydrogen back from H3O plus and forming HF and water. So this is a very reversible reaction and form equilibrium as we've talked about in the past. And since that reaction happens in the reverse direction, you still have some reactant, a lot of reactant, to be honest with you, at your disposal. So, kind of a summary: strong acids are really great conductors. Weak acids are pretty good conductors. Strong acids ionize completely. Weak acids ionize somewhat, but not much. And I think that that's probably a good kind of way of thinking of these two things. Let's recognize, though, the counterintuitive nature of this definition. In chemistry, strong means breaks up completely. Weak means stays together mostly. Okay? So, how do you know if an acid's going to be strong or weak? The answer to that is simple because it's not simple. Here's what I mean. There's not a great way to tell if an acid or a base is going to be strong or weak. So there just happens to be not many of either one of these. And so, what we generally will say is that the 6 acids listed here and the 6 bases listed here characterize our strong acids and our strong bases. So, perchloric acid, hydrochloric acid, hydrobromic acid, HI, hydroiodic acid, nitric acid, sulfuric acid. Those are the strong acids. Every other acid that you ever run into, chances are it's weak. Strong bases, we have some hydroxides. And I think the easiest way to remember these is as follows. Lithium, sodium, and potassium, these are all group 1, first column hydroxides. Calcium, strontium, and barium hydroxide, these are all group 2. So it's kind of easy to remember that. For the acids, the way I remember it is there are 3 binary acids with that hydro prefix: hydrochloric, hydrobromic, hydroiodic. And those acids are generally going to be strong. The other 3 that we have listed here, the way that I tend to remember it is they have many more oxygens than they do hydrogens. So here, HClO4 has three more O's than H's, 2 more O's than H's for nitric acid, 2 more O's than H's for sulfuric acid. And really memorizing them is kind of the best way. All right, let's come back to the Google Meet and talk before we move on to our next topic.